We're getting very close to the end of the course. The main target now is to finish off the proof of a version of Szemerédi's theorem for subsets of fp to the n when p is at least 5. So let's just remind ourselves where we have got with that up to now. We had started with a dense subset A of fp to the n, and if we let f be its balanced function, then we have one result that says that if f has a small u3 norm, then A definitely contains progressions of length 4. So we can assume that f has a large f3 norm, and now the aim, as in Roth's theorem, is to try to find some substructure. In this case it'll be an affine subspace on which f has a large average, or equivalently A has a larger average than or has increased density. So what we'd managed to get so far was that, so let's just go back and look at the statement of the last lemma that we proved, that if we start with a function f that has u3 norm to the 8 at least c, sorry, that's not what I wanted to say. Here we are. The assumptions are that the L infinity norm is at most 1, and the 8th power of the u3 norm is at least c. And then by an argument that exploited the box norm in a crucial place, although it doesn't have to, there are equivalent ways of doing it, we ended up with the following rather strong statement, which is that we can find a dense set B such that if you restrict and a function phi, let me just, with the following properties. So perhaps I will actually just write these properties as a part of the recap. So the key properties of phi, so we have f was defined from G to C, and then we have a set B which is a subset of G, and we have a function phi from B to fp to the n, and the following properties hold, that 1 for all A in B, the Fourier coefficient of f at phi A squared is at least c over 2, if I remember correctly, and 2 there are at least c over 2 to the 8 g cubed quadruples a, b, c, d in b to the 4th, such that a plus b equals c plus d, and phi a plus phi b equals phi c plus phi d. And we'll see why that is helpful, but before we do that, let's just observe that if we set gamma to be the graph of phi, so the set of all x, or let's call it a, phi a, such that phi belongs to, such that a belongs to the set B, then gamma contains at least c over 2 to the 8 g cubed additive quadruples, because a quadruple with this property is precisely the same as an additive quadruple inside the graph gamma. Now notice that gamma has size less than or equal to g, so this is saying that we've got a lot of, within a constant of the maximum number of additive quadruples, and so it's Balog-Szemerédi time. So I'm now just going to run through a sequence of steps just exploiting some of the results that we proved earlier in the course, and of course that was a large reason that they were proved earlier in the course. So and also I don't want to get too hung up on bounds now. I will just make a global statement that these arguments can be done in such a way that you get fairly good bounds at the end of the argument. But if you really want to make an effort to squeeze the best bounds out, it'll just make all the arguments look a little less pretty. So I'm just going to sort of have constants C1, C2 and that kind of thing that you can just believe me depend in not too terrible a way on the initial constant C. So by Balog-Szemerédi, gamma has a subset gamma 1 such that gamma 1 minus gamma 1 is less, I shouldn't have said this first, but is less than or equal to C gamma 1, where C depends only on little c. Let's call it C1. And gamma 1 is greater than or equal to C1 times the size of G. So it'll have some dependence on this C over 2 to the 8. It'll be a fairly large power of C, but and this one will be a fairly large power of 1 over C, something like that. So now, by Freiman's theorem, gamma 1 is contained in a subspace. At this point, by the way, up to now I've been talking about an arbitrary finite abelian group. I should have said this at the beginning. Well, actually, up to now I didn't need to say it. So now let us just look at the case G equals fp to the n. I'm still going to call it G sometimes because it's more convenient than writing fp to the n, but it is fp to the n. So by Freiman's theorem, I don't have subspaces if it's not fp to the n. So it's contained in a subspace. What shall I call it? Well, I'll call it V of G squared, considered as a vector space. So fp to the n squared, which is looks like fp to the 2n or something. With the size of V less than or equal to C2 times the size of G. Now, a little comment here. If you dig into the proof of Freiman's theorem, what we actually did was find one subspace that had the property, a sort of smaller subspace, let's call it W, such that gamma 1 was contained in W plus K, where K was a set of bounded size. And then we said that W plus K must be contained in some subspace V, and because K has bounded size, V has a dimension not too much bigger than W. If we use that, then we get a worse bound than if we just pass to a subset gamma 2 that's contained in some translate of W, and by averaging we can get at least we can get a reasonably large chunk of gamma 1 that's contained in a single translate of W. But I'm not going to worry about that little refinement because I'm not worrying too much about the bounds. I'm just making the comment that it's actually quite easy at this point to do a little bit better than I'm doing here if you care about the bounds. But since I don't, it's simpler just to quote Freiman's theorem in its entirety. So what have we got there? Well, now let's let V equal V0 plus V1, where V0 is the set of all naught y such that naught y. How can I put this? I'll put it a slightly nicer way. It's a sort of set of all x, y in V such that x equals naught. And V1 is a complementary subspace. So we get that the size of V equals the size of V0 times the size of V1, but also the size of V1 is at least as big as the size of gamma 1 because two elements of gamma 1 can't differ by an element of V0. So we look at all the cosets of V0 inside V, and each element of gamma 1 has to belong to a different coset, and therefore size of V1 is at least the size of gamma 1. So that tells us that V0 times the size of gamma 1 is less than or equal to the size of V, which is C2 times the size of G, which implies that since gamma 1 has size bounded below by, what was it? Did I say C1 of G? So that implies that V0 has bounded size. So that's C3 of times this. So there we go. We'd have a set that's not too big. And so now partition V into cosets of V1, and by averaging we find some y such that, and these cosets might as well be cosets where you use vectors in V0 to translate V1. So we find some y such that V1 plus 0y intersect gamma 1 is greater than or equal to C2 times the size of G, because the total number of these cosets is bounded by C3. Between them they cover gamma 1, so at least one of them must be of at least that size. And then let B1 be the set of all x in B such that x, phi of x belongs to V1 plus 0y intersect gamma 1. And then there is a linear map psi that agrees, sorry, affine map, I beg your pardon, that agrees with phi on B1. And how's that defined? It takes x to the unique y such that xy belongs to this, not y, because I've used a y, unique z such that xz belongs to V1 plus 0y. So there's a unique z such that it belongs to some subspace, and that's easy to check from that this map, defined slightly implicitly, is actually a linear map. So recalling that, so we know that for all A and B1, because B1 is a subset of B, we have that partial AF hat of phi A, and hence psi A as well, because phi agrees with psi on B1. That squared is greater than or equal to C over 2. So, putting all that together, we get that if we take the average over all A, not necessarily A and B1, but the ones in B1 are going to be the ones that we know contribute to this average, of this Fourier coefficient, that's going to be greater than or equal to, let's call it C3. So it's at least C over 2 whenever you're in B1. B1 has size, I've lost the size of B1. I didn't actually say the size of B1, but oh yes, no, B1 has size C2 times the size of G. So this is going to be some C3 is going to be something like C2 times C over 2. And now I'm going to expand that out. So psi of A is a linear map, remember. So we get that the average of A, well, let's just say what I'm doing. So expanding the average of A, and I think by now we've done this enough times that I think I can do it in one go. So the average over X and Y of, so fx minus A bar, and I'll do the omega parts later on. So then f of y bar f of y minus A, omega to the minus psi A dot x minus y. That is greater than or equal to C3. And now I'm going to change variables a little bit, so that's average over x A B f of x minus A bar f of x minus B bar f of x minus A minus B omega to the minus psi of A times B is greater than or equal to C3. So B is x minus y. Now that's quite nice. We've got a nice sort of additive quadruple sitting in there. And here we've got a bilinear form in A and B. So I've taken an affine map, psi of A, and dotted it with B. Now let's suppose that psi of A B, what should I call it? A of A plus U or something. So A is a linear map, and U is just some vector, which makes it an affine map. So then we have so I'm just going to rewrite it slightly. I'm doing this because I know where this is going. So f1 of x, f2 of x minus A bar, f3 of x minus B bar, f4 of x minus A minus B, omega to the minus AA dot B greater than or equal to C3. Now I should also, if I hadn't had these f1, f2, f3, f4, have a contribution. So let's just write out what I sort of started with. I started with omega to the minus AA dot B minus U dot B. But I've absorbed the U dot B into the F and an F by thinking about observing that u dot b equals x dot b, equals u dot x minus u dot x minus b. So if I multiply that by an omega to the minus, if I multiply that by omega, yeah, so where f1x equals f3x equals fx omega to the u dot, no, omega to the minus u dot x, and f2x equals f4x just equals f of x. So f2 and f4 are just f, and f1 and f3 are f modified by this linear amount, which, as we shall see later, I don't really mind doing. And so we now have this inequality here. You might think there ought to need to be a mod sign around it, but it just so happens that it's non-negative because it was equal to something where we did have the mod signs. Now, there's a very nice thing that we can do here. This is a bilinear form. If we have a symmetric bilinear form here, but we don't have a symmetric bilinear form. So what I'm going to do now is do a nice little trick that was invented by Ben Green and Terence called the symmetry argument. So I'll just write this as slightly different. I'll say C3 is less than or equal to, and I'll put a mod sign around now, because so supposing we have this, that actually weakens my hypothesis, but that's okay. And in fact, I don't really need these bars here, because I could just change the definitions of f2 and f3. But it seems so unnatural not to put the bars that I'm putting them. So here we've got a bilinear form in A and B. So we're going to suppose that this is the case. And what I'm going to do is, roughly speaking, show that we can just replace this by a symmetric bilinear form. So that sounds a bit too good to be true, but we'll see how to do it. So what we're going to do is first of all do a clever change of variables, and that's really the main idea. After that, the steps are reasonably standard. Maybe not to you if you're doing this subject for the first time, but within the subject. But the idea of using this change of variables and that it would be helpful is a very nice one. So we're going to set, let's say, z. So we're going to think of these as the vertices of a parallelogram: x minus a, x minus b, x minus a minus b. So z is going to be the center of the parallelogram. So z is going to be x minus a plus b over 2. And then u and v are going to be the vectors that you need to get from the center to the vertices. So u will be a plus b over 2. So if I add u, I'll get to x. If I subtract u, I'll get to x minus a minus b. And v will be, not surprisingly, a minus b over 2. So if I add v, I will get to, well, let's just do that in a moment. So C3 is therefore less than or equal to average over x, by the way, this change of variables requires my p to be odd, because I'm dividing by 2 all over the place. So z u v f1 of z plus u, f2 of, now what is x minus a? That's that's z minus v. And x minus b is going to be z plus v. And x minus a minus b, as I've already mentioned, is z minus u. And then omega to the minus b. Now we've got to express a and b in terms of u and v, which is not so hard. A is u plus v, and b is u minus v. And this equals, now what I'm going to do, so by averaging, and the triangle inequality, there exists Z such that C3 is less than or equal to the average over U and V, F1Z plus U, F2Z minus V, F3Z plus V, F4Z minus U. So exactly the same thing that I wrote up here, minus B, U plus V, U minus V. Now what next? I now want to note that I can write this, so Z is now a constant, I've picked a Z. So this depends only on U, this depends only on U, this depends only on V, this depends only on V. So I can write it as follows, that U and V, F of U, G of V. But I can also absorb some of this stuff into F and G. So the minus, this splits into four parts, minus beta U, plus beta VV, minus beta UV, plus beta UV, minus beta VU. So the beta UU part I'm going to absorb into F of U. So that F of U is going to be defined as F1Z plus U, F2Z minus, F4Z minus U times omega to the minus beta UU, and G of V and so on. So it'd be like that. So then I get omega to the minus alpha UV, where F and G are some functions. Well, I'll write out what F of U is, but I won't bother with G of V. So Z plus U, F4 Z minus U, omega to the minus beta UU, and similarly G of V, and alpha U of V is an antisymmetric, that's why I use the letter alpha, beta UV, let's make it plus, just to make this what I'm writing here true, beta UV minus beta VU. Now this, I hope you notice, is a function of two variables times a function of one variable times a function of one variable averaged over the two variables. So we can use the box norm inequality. So by the box norm inequality, omega to the alpha box norm is greater than or equal to C3, because we get the box norm of this times the L2 norm of this times the L2 norm of this, and these have an infinity norm at most 1, so they certainly have L2 norm at most 1. So we get this. So now let's think a little bit about what the box norm of omega to the alpha is. Actually, I recommend... no, I'm not going to tell you what the box norm is because it's an exercise on the sheet, or rather I'm not going to prove this next step. I'm just going to, sorry, what I mean is I am going to tell you. So the box norm of omega to the alpha to the fourth is p to the minus r, where r equals the rank of the bilinear form alpha. And if you're worried about being left with something as an exercise, I guarantee you this is not a particularly difficult exercise. It's actually a rather instructive exercise to do. I strongly recommend it. So p to the minus r is greater than or equal to c3 to the fourth, which means that r is less than or equal to 4 log p of c3 to the minus 1. c3 is just some constant, so that tells us that the rank of the bilinear form alpha is bounded. And the moral of what we're going to do is that very low rank bilinear forms don't bother us too much. So the antisymmetric part of the bilinear form beta, which is alpha, is not too worrying. And it's only the symmetric part that we're left with in a certain sense. So what we're going to do is pick a subspace V such that alpha x y equals naught. Oh, sorry, I haven't said, well, I'll say it, but it's going to have low codimension. So for x in V and y in fp to the n with a codimension of V equals R. And then one can check quickly that alpha is constant on cosets, products of cosets. I'll justify this in a second. Of V. So supposing you look at alpha V1 plus, what should I call it? W V2 plus Z, then alpha of V1 of the whole of this lot is 0 because V1 belongs to V, and so we're left with just alpha W V2 plus alpha W Z, but alpha W V2 is minus alpha V2 W, so that also is 0. So the only bit that's left is alpha W Z, which is constant on the cosets V on the product V plus W cross V plus Z. So that's supposed to be the value of a value of alpha in this product of cosets, and so it's constant. So where does that get us? So let's go back to the expression that we had up here. So first of all, we can write beta equals alpha plus sigma over 2 where sigma xy equals beta xy plus beta yx. So alpha was beta minus beta, so that's the antisymmetric part, and well, it's not the antisymmetric. When you divide it by 2, it's the antisymmetric part. So we get, now just looking back at this expression, going back to where we were right up here, we have that C3 is less than or equal to average over XAB fx minus a. That's why f2 f3 x minus b f4 x minus a minus b omega to the alpha ab or minus alpha ab minus over 2. But now we're going to apply the triangle inequality and say that's less than or equal to the average over all UVW of, it's going to, I'm not going to be able to fit this into one line, but anyway, the average over X in V plus U, average over A in V plus V, and the average over B in v plus w, so I'm just restricting this thing to a particular product of cosets, so x in one coset A in another coset B in another coset of f1x, f2x minus a, f3x minus b, f4 x minus a minus b, and then I get omega to the minus beta ab over 2, and I'm just going to put the end of the modulus sign there. So you say, what's happened to alpha ab over 2? And the answer is that was constant, so it just had modulus 1 and didn't change at all according to the change in a and b, so I can just take it outside the modulus sign as a 1, in which case it just vanishes. So that's what the symmetry argument does. The symmetry argument has now allowed me to get rid of the antisymmetric part. Oh, and I didn't mean to call it, this wasn't beta, of course, this was sigma, and be left with the symmetric part, sigma. So I think I'll stop this video here. In the next video, I will show you how to exploit, I'll show you what we can do when we've got a very nice looking symmetric bilinear form in there. And we're not far off now from obtaining the density increment that we need in order to complete a proof of Szemerédi's theorem for progression to length 4 in fp to the n.